All right, we're finally back. It is game 2005. That's game physics here at George Brown. And it's still officially the fall 2017 semester, even though we're in winter 2018. And like I said, we're talking about collision detection today. Next week, collision response. Let's talk about this a little bit. This is neat. I can make it actually a lot bigger than before because of my projector. Woohoo! All right, so we want to talk about collision detection, and one of the things we want to talk about is how we incorporate collisions and physics together. One of the things we want to try and do to make it work well for our games is we got to make collisions believable, somewhat realistic. I have to kind of pose the question, what is good enough for realistic collision detection, collision response? Today, we're going to be talking about collision detection. So it's like, how do we detect a collision in 2D and 3D space, right? So again, we got to do a couple things. One of them is there's two objects. They can't occupy the same space somehow, whether it's in a 2D plane or a 3D plane, right? And either we're going to push them apart or we're going to make sure that they stop when they're moving, okay? And the other thing is, after we collide, right, we need to respond as though the laws of physics are taking hold, okay? Now, this is one part. Now, if you're playing a 2D game where there's no physics, for example, a top-down game, you may not need to do the second part, like bouncing off a wall. You may not need to do that unless that's the kind of game you're making. But for 3D games, most 3D games, whether they're third person or first person, physics is part of the game. And so we want to be able to do collisions and responses to collisions that make sense. So there's a couple of phases when we do collisions. There's a broad phase. And what I mean by this is if we were starting to do collision detection every frame for thousands of objects on the screen all at once, right? Our performance would be really, really poor because there's like thousands of objects and I'm trying to check to see if I'm colliding with all of them. So typically when we have a lot of objects, right? More than, let's say, 30 or 100 objects on the screen. And especially when you're working on the web, we want to break it down into this broad phase, narrow phase type of collision, okay? By the way, I haven't shared the PowerPoints. I will put them up on Blackboard later today. You'll see them, but you can watch the video as well. So we have this idea of this broad phase collision. So where we kind of break up our world into a grid, okay? That's one way of doing it. We can also use something called the spatial hash, right? Which is more of an advanced method of splitting things up. There's other ways of doing things with octrees and a bunch of other stuff that you can use for collision detection. But pretty much what we're going to be doing when it comes to collision detection or collision response is, hey, I'm going to wrap a standard shape around my object. I have a spaceship. Let's say it's pointed like an arrow. I'm going to wrap some kind of basic shape that is very close to that spaceship. And there's going to be two types. Mostly we're going to be using things like spheres or circles in 2D and cubes or boxes in 2D, right? Depending on whether you're in 2D or 3D.
Need to be like that. If it's going to be like a 3-point pyramid, for example.
You can do lots of stuff. You can also combine those kind of any primitive shapes. For example, you can use spheres and some kind of cylinder to make a capsule, as an example, right? There's many ways you can do it, but you can use primitive shapes. We want to surround our object with primitive shapes in order for us to detect collision, okay? That's typically how we would do it, okay? So that's the most typical. And in broad phase, before we do any kind of detection or even try to detect, we want to know where our objects are in 3D space or 2D space. So imagine if I did I'm detecting an object like, let's say James is over there, right? Way over there in the back. Hi, James. Right? James, if he's going to try and throw a punch at me right now, like we're in a melee kind of game, and James, throw a punch, James, throw a punch. Go ahead. Oh, yeah, he missed, right? Do I have to start detecting James's punch from way over there? No, right? Because he's too far away. So broad phase, we break the entire room if they were doing this into a grid system, right? And we say, hey, James is too far away. Even if he's trying to punch me, if he's a zombie punching me or something, or trying to claw me or eat me, my brains, right? It's not going to happen because he's way too far away. So why am I going to check collisions with him, right? But as I get closer, let's say Hercules over here, right? Hercules, right? Hercules, throw a punch on, go, right? Hercules can probably hit me. I'm a lot closer to Hercules, right? Still, he's too far away where I am now, back behind my podium, and he's at his desk, right? And if I'm really close, if there's somebody right here in my space, Emma, if you want to punch me, come over here, and you can in my space, right? Now you can punch me about Star Wars. Star Wars sucks. See, I even recorded it on YouTube. All right. Anyway, so it doesn't matter, right? If it was, unless there's someone that's pretty much within your square, within your grid, right? There's no need to check collisions. Now, there is a positive and negative around this kind of approach to thousands of objects, right? Which is you get inconsistent performance sometimes. Okay, example, if I have thousands of objects on my screen, but I'm not going to check, right, unless they're really, really close to me, right? And let's suppose all the thousands of objects are where you are, right? And then they start coming closer to me. Now I'm doing a lot of checks. I do thousands of checks. I wasn't doing checks over here. I was moving nicely. But now I'm starting to do a lot of checks. What's going to happen to me? I'm going to slow down. The entire system is going to slow down. So I'm going to have inconsistent gameplay, right? I'm going to have really good gameplay when you're way out there where nothing's close to me. And then as they come closer, the gameplay is going to slow down to a crawl. And that's bad, right? That's really bad. We have this inconsistent kind of like curve, right? So sometimes what we do, especially when you don't have a lot of objects, if I have 30 objects on the screen, even in a web game, I'm going to always check collision. I'm not going to do broad phase, narrow phase, so that I can stay consistently bad, right, all the time, right? So that it provides a consistent performance or experience to the user, right? Even though it's bad, it's not as bad as being really good over there and really bad over here, right? That makes it almost unplayable when you're close to me. Now, in most modern systems, if you're using C++, this makes sense because it actually helps performance. It actually makes it better when you have broad phase, narrow phase, especially in 3D. That's when we use broad phase, narrow phase kind of idea. And this is the concept that I'm talking here. In narrow phase, this is where we do all of our work. Now, whether you include a broad phase or not, you need to do some kind of narrow phase where the space between you, the gap between your object, your player object, and the rest of the world, there's a narrower gap, right? A much smaller gap than the large gap between me and, let's say, James, like way over there, right? He's too far. Or even me and Hercules now, where he is right now. It's still quite a bit of a gap. There's no need for me to check collisions. But maybe there's a need for me to check collisions with my desk. Here, if I bump into my desk, I should be able to check collisions just within my realm of influence. My, if you want to call it, kind of a, my area that I'm in or whatever, right? So, so that's for some. So narrow phase is where we do our collision checking. And the most basic type of shape that we can use is some kind of, because remember I talked about wrapping your object in some kind of basic primitive, is the sphere. Okay, I want to take my sphere shape and I want to put my random object inside that sphere. Now it's got to be tight around the sphere. So it can't be something that is, irregularly shaped. If it's more spherical, the more spherical my object is, the more accurate my collisions are going to be. But the more squarish my object is, if I put it inside of a sphere, then there's going to be less efficient collision detection. In 3D, it's almost unnoticeable when it comes to a player versus another player interaction. It's really noticeable where there's a player versus a wall interaction. Like an example, I've got a sphere collider somehow, and I'm touching a wall, and you know what? I can't get near the wall. Even if I wanted to, I'm not striking the wall. Or even better, I'm going through the wall, right? Which is really, really bad. I don't want that. But in 2D, it's really, really apparent. If I use a circle collider, because now I'm taking my sphere, I'm projecting it onto a 2D plane, it becomes a circle, right? And I wrap it around a shape, whatever the shape is, some kind of cloud, or whatever I want, right? Then what ends up happening is I have this phenomenon where I have which we talked about before, and some of you, when you had me in your Game Production 2 class, I talked about this idea of a logical collision versus a visual collision. We don't have a visual collision sometimes if the object is outside of and I'm going to give you an example in a second, right? But we have a logical collision because my code is telling me that it should collide, right? So it looks weird. It looks like, hey, I shouldn't have got hit there, but I'm getting hit because I've put some kind of basic shape around my my game object. Okay. By the way, as if you notice, we've moved away from physics for today. right? We're not talking about physics, we're not talking about math yet. We're talking about programming and how we can apply stuff we've known. This is the application phase. We apply our physics to this stuff. That's why these 2 days, if you will, this today and next week, are pretty critical in terms of understanding, because you need to pass this forward in your game making skills, right? All right, so here's an example of that. I got this little bunny rabbit. He's made in 3D, as an example. And what I want to do is I want to wrap the bunny rabbit in this sphere, right? Now you can see that there's a lot of spaces in here, right? Like here, as an example over here, where there's no bunny rabbit, right? So if I was to enter this area, if this is a bad wrap, for example, this is not the tightest object I can use, right? Then what's going to end up happening is I'm probably going to miss the bunny rabbit sometime visually, but hit him logically. So my calculations are going to say, you hit. Visually, we're looking at it, we're like, wait a minute, there's no hit there. What happened? That game cheated me. I'm not supposed to get hit here, right? Skyrim is a great example of that. Anyone play Skyrim? Okay, I just played it recently. I was saying I kind of binged out over the holidays for whatever reason, this older game, right? But I got it on special. I think it was like someone bought it for me for $30 or whatever on the PlayStation Network. And if you ever play, like kind of a sniper with Skyrim, right? You walk around the corner, you've got your bow kind of ready to go, and just walk barely so that you can see your reticle, right? And it's on the enemy. You're in stealth. I'm just kind of framing it for you, right? And then you let the bow go. You let the string go, right? And it hits the corner. What? I wasn't aiming there. I was aiming at that guy. I can see him. My reticle's on there. I should hit him, not the side of the barn that I'm hitting. I'm kind of hiding behind the barn. I'm kind of peeking over like this, right? But I'm not going to hit, Hercules here. I'm going to hit here, right? Doesn't make any sense. And the reason for this is because the way the colliders are working, the way the game has been designed, right? And the way what I'm looking at, remember, it's just an illusion, right? What I'm actually looking at and what's really happening is totally 2 different things, right? So part of it is the colliders, part of it is the way that the game interacts and all that kind of stuff. And so we want to get a shape that makes the most sense when it comes to collision detection. I want to wrap my object in the best shape possible. That's why most modern game engines that you get off the shelf, example Unity, right, or even Unreal, have different kinds of shape colliders you can use, like a sphere collider, a capsule collider, some kind of cube collider, or rectangular collider, or something like that, right? There's also other kinds of colliders that are more complex that Unity uses, for example, some kind of mesh collider, which is really great for convex objects, right? Sorry, concave objects. Convex objects, you should really use a combination of colliders, right, of basic shapes that you kind of put together to create your bounding box idea, as opposed to using a mesh collider. Mesh collider is very, very expensive, right? And the reason why is because you're making a mesh, an array of points that you're saying, hey, if it's within this distance of this point, collision, right? If it's within this distance of this point, collision, right? That's crazy ass. That means that you have, instead of making a, kind of a central point, like the idea of a sphere is you're going to use, all you need is 2 things for a sphere, right? You need the radius, that's for sure, right? And you need the central point, wherever that central point is. Those 2 pieces of information of a sphere is all you need. And then you can provide this spherical collision kind of system, right? But with a mesh collider, like imagine this mesh had each of the vertices was a collision point, right? That's crazy, right? That means that each point, each vertex inside my polygon is going to be a possible collision point. So now I've just multiplied my collision checks by a bunch of, however many vertices there are. It might be something like 50 or 100 vertices, right? More accurate collision, way lower performance, right? If you're doing a physics simulation, though, you may want to do a mesh collider or something like that because you want to be as accurate as possible. If you're making a game, you got to really figure out what's good enough. Okay, that's what I want to put in your mind. What's good enough? So here's an example of this sphere or circle collider. You have these 2 circles. They have a radius. Each circle has a radius. Each circle has a central point. There's a distance between the 2 circles. And really what you want to do is say this. If D, the distance between the 2 circles, is less than, right, the radius of both objects, right, combined, then I have a collision, right? Because that means that these 2 circles, one circle is inside of the other one, right? So here's this radius, and if you notice if it stretches to here, and this radius stretches to here, So if I combine these, I add R1 plus R2. If I take these two things, R1 plus R2, I can say that if D, the distance between the two center points of each of the circles or spheres, you can, by the way, you can extend this to the sphere example, right? If it's less than, right, the radius between from the center point, right, both radius combined, radii combined, then you're good to go. You know you have a collision. However, it's easy, the easiest way to detect collisions, but the least efficient. Not from a performance perspective. Performance, you're going to get great performance on this because it's not allowed to check, right? But we're going to have this problem with logical versus visual collision problem, right? Like it's going to look, sometimes it will look wrong. Now, combining shapes, right, gives you like the idea of having more than one collision check, right? But you don't want to use a mesh type collider unless you absolutely need to. Like you want to 100% cover your shape for whatever reason. Combine shapes, make different shapes. Like for example, if I have a character, maybe I'll put a circle or sphere collider on his head, right? And some kind of box collider on his body, right? Depending on how it goes, yeah.
So if you have kind of a complicated object, would it be more efficient to put like 40 boxes on it instead of one?
It depends.
Like that?
Yeah, it depends. It might be. It might be. Yeah,
okay.
It might be, or more than one sphere, a bunch of spheres all over the place, right? Now there's a point of diminishing returns, right? The more we use, then the more checks there are, then you're almost at the point where you're going to use a mesh collider or something else or another mode of collision detection. And there's a couple of ways we can detect collision. This is one of the most common ways. And by the way, guys and girls, I highly recommend this way as a starting point, right? If you're testing a game and you're making a prototype, start with this one. Even if there is visual versus logical collision issues, right? You know you can test your game. You can block out your game. You can start testing. You can start playing. For alpha or for first playable, this type of collision detection system is just fine. Okay, it's going to work just okay. All right. Remember that there's the big rule that I've learned last year in 2017 that I want to pass to you as I was making my games and stuff is don't make a game engine, make a game, right? You know, the game engine's out there, use whatever you can. I like the idea of minimum viable product, especially because as we're all entrepreneurs in the small game space, that's where we all are. At the end of the day, we want to sell our products, right? Or sell ourselves one way or the other so we can become part of a Ubisoft or make our own little game studio, right? Minimum viable product. Don't think about making a game engine. The game engine will arise. It'll come out of your product, okay? Make your game. Make it work. Make it fun, right? Focus on that stuff. Which is a little bit contra because, you know, some programmers are very analytical and we all think about, I want to be as accurate as possible. I want to make the best class possible. I don't want to use inheritance somehow. I want to use multiple inheritance with C++. I want to do, you know, some kind of entity component system. I want to make whatever. And once you start going down that road, you're not making a game anymore. You're spinning your wheels and making a game engine. Don't do it, is what I'm saying. All right. So here's an example of some code, right? We got some code here that I want to show you, right? By the way, I've made some references to some of the places I took the code. I didn't write this, but it's almost exactly what I would use anyway if I was making it, okay? So here's an example of, I've got this circle 1 and circle 2. We've got a radius of 20. I've got X and Y coordinates of 5 and 5 for the first circle and 10 and 5 for the second circle, right? And what I want to do is I want to make the difference. Notice that it says dx and dy. It's just a shortcut for saying, hey, subtract the x's and the y's from each of the circles. So you have this idea of a dx and dy. And then all this is down here is Euclidean distance. If you think about these three lines, line 4, 5, and 6, Euclidean distance, which is what we covered actually in the early part of our course, way back in 2017, September, right? I know, it's like back in the day now, 20 weeks ago. So way back there is when we covered this stuff and we're saying that basically, hey, this is the distance, right? And if my distance is less than the 2 radii combined, I've got a collision detection. This is almost the exact code that you need. It's pseudocode though. It's not written in any particular language. You can take this code and use it in any of your games and it will work, even in Unity, if you don't want to use their colliding system. Okay? So very, very simple code. This is the way we would evaluate stuff. I think it's pretty succinct, and I've used this kind of stuff all over the place. Now, typically, you know what? I probably wouldn't write it like this. I probably would have either a math library in C++, I might use GLM, right? And GLM has distance calculations, magnitude. In Unity, it also has vector, different vectors and different vector objects and so on that you can use that are built in. You don't have to make your own distance class if you don't want to, right? In JavaScript, you do if you're making it in some kind of web game, right? Although there's math libraries out there too. For example, what is it? GL Matrix, if I'm not wrong, is something that's out there for JavaScript as well. So there's different libraries out that work for different platforms. I recommend, you don't have to write them. Here's the bad thing. Whenever we write square root, right? Here's an example of our square root. This is one way of doing it, right? But this is bad because we're doing square root calculations every frame, right? Square root is very expensive. So when we're doing this kind of stuff, there are other ways to do it. We can use the squared distance as opposed to the square root. So instead of using Euclidean distance, we can use the squared magnitude between the two objects, right? We have two vectors or 2 points in space, and I want to get the squared magnitude. So I'm not using the square root here. I'm just multiplying dx by dx, dx times dx, or dx squared, plus dy squared, and that's the squared distance. And now I got to square the radii, right? So if I take that and square the radii, everything is squared, which means you're going to get like for like, and you can avoid, to some degree, using square root. Okay, we want to try and avoid using square root as much as possible. All right, so that's a very basic way of doing things. Okay. Remember that you can also do the same kind of idea with a vertical cylinder, right? So I have a vertical cylinder, and it's very much like a circle. I've got 2 circles, one on the top and one on the bottom. I still have a radius, right? But the additional thing I have with the cylinder, because it's in 3D space, is the length, right? So I can take the length of the cylinder, and I can incorporate that into whether or not I have a collision if you hit the ends of the cylinder, right? Now, if we've got spheres and I've got a cylinder, here's basic shapes we're talking about, right? Then I can make a capsule. And once I have a capsule, I can make a character in 3D space, just like I would if I was using Unity. I can have a capsule collider. And basically what I'm having is I'm combining basic shapes to make a more complex colliding system. That's all I'm doing. Still way more effective and efficient than using a mesh of some sort or another. I want to avoid a mesh as much as possible. Any questions so far about using primitives? Yes. Faster than a capsule collider? Yeah, well.
Given line, like any distance from that line.
Yes, there's different ways of approaching it depending on how you construct your capsule. Right? If you make your capsule with math, like actually create it and define your capsule with math, fine. You can make the radii from the ends and so on. But I'm saying, let's say, for example, I made a sphere collider and some kind of cylinder collider, and then I can make my capsule collider from there. I'm just trying to build it up for you guys so you can see how it works, right? And instead of a cylinder, if you're really scared about how to make a cylinder or you don't know how, use a cube or some kind of prism, rectangular prism, right? Which is almost very similar to a capsule. It's just a square capsule, right? Which is totally fine. And what I mean by that is, I'm just going to use Blender as an aid for a second. So I'm just going to pull up Blender here, our free program. So I've got so here's an example of an object that I'm going to bring up into space here. I've got a cube. And let's suppose I'm just going to go into edit mode here and modify some of the verts, right? So I'm just going to move this a little bit down, a little bit, and zoom out, and maybe move this around. So it's not just a cube anymore, right? So you can see that it's some kind of weird object, like maybe some kind of, I don't know, weird asteroid in space, a pointy asteroid. And I've got this thing, and I want to be able to collide with it, right? What I want to do is, again, wrap it in some kind of object, right? Now, if I was to wrap it in another cube, so let's add another cube, and let's make this cube bigger, right? And just to make it so that you can see inside the cube, I'll use some kind of wireframe, and you can see that it bounds the object, okay, but they're going to be, it's just too big, right? So I'm going to have to try and make this cube as small as I can, so it kind of bounds the object. Now, you can see that I haven't really centered the cube or whatever, and I can probably flatten this cube, so I can kind of scale it along the z-axis here, so it's a little bit, not as tall, and so on. and I can maybe scale it along other axes, you can see that part of it might stick out, like this little part over here. See if you can see that. And again, just for demonstration purposes, you can see this, right? You can see that this little edge peeks out and so on, and I could try and get as more accurate as possible. But at the end of the day, I want to try and use some basic primitive to box my shape. If I'm making a capsule, I'm just going to start off a new project here. If I'm making a capsule, again, what I could do is instead of using this, I can make a cylinder, like I said. So let's just get rid of this. And let's add ourselves a new cylinder. Nope. Cylinder, I'll be okay. There's my cylinder. And typically when I work with something like Blender or Maya, I want to remove the cap, the cylinder cap. And on the left-hand side, it's hard to see here because I'm projecting. Well, you can see that the cylinder fill type up here is Ngon. I can change this to none. And I can, this way I don't have a fill for the cylinder top. Depending on how smooth I want my cylinder, when I'm making my object, I can make it less faces. Right now there are, I believe, 32 faces. I don't need 32 faces typically. I can go down with something like 16 when I construct my cylinder. So you can see that it becomes a little bit coarser, but still pretty good. I mean, you can see that it's not so bad, right? And then I can add a sphere or two. So I can add some kind of sphere. I'm probably going to add some kind of icosphere and on the top, or some kind of even, maybe let's add the other type of sphere that we have there. Just to give you an example of that, a UV sphere, which is a little bit smoother. Actually, I'll undo that change. And just one thing I forgot to do is I want to, with my UV sphere, reduce my count as well. So instead of 32, I'm going to go down to 16, just to form it out for you guys so you can see it. So you can see my sphere is where I'm making my cylinder, right? That's how I'm doing it. I've got my sphere top, and I'm going to kind of duplicate this. So Shift D for duplication, and I'm just going to go along the Z axis again. I'm going to bring my sphere so that it's the bottom is kind of the bottom right there. And you can see that I've created some kind of capsule out of two spheres and a cylinder, right? Now, there's nothing wrong with this kind of stuff, but you need to have control of your primitive shapes. You have to kind of create primitive shapes in memory. You don't have to actually render them. So these don't have to be rendered anywhere, of course. You wouldn't want to render these things. But you can surround an object, a character, or whatever. And this is a great way to surround an object or character, especially in 3D space, because they're pretty good. It's probably good enough for most of them, okay? And why am I saying that? Even if it's a 3D animated character, if you're inside of some kind of capsule like this, for the most part, you're okay. All right, so that's what we're really talking about here. We got some kind of vertical cylinder, we got two spheres, and we have a capsule. And the idea that we want to do is we want to talk about each of the vertices in order for me to get the, kind of the object's origin point. We can use the sphere for that, or we can use some, even if we're doing a cylinder, we loop through each of the vertices, and I see that I've got like nice spelling errors too. Thank God I'm now. And this idea of I want to make calculate the distance between centers. Okay, any questions around basically this idea of sphere collider or distance calculation? I'm using distance to calculate if I'm colliding between two objects, two shapes. Okay, this is collision detection. All right, well, what about, so again, we talked about positive and negative. On the positive side, it's really easy to do. On the negative side, not very robust. Different than efficient. Robust means, again, I'm going to have this problem between visual and logical collisions that's going to occur. How about this idea, instead of spheres, we can also use something else called bounding boxes. Okay, we have bounding boxes. And bounding boxes are great if you're living in a square world. Example, you're playing Minecraft. Bounding boxes are everywhere, right? I mean, you can collide with everything in Minecraft. You can break everything in Minecraft, right? And it's very simple. Collisions are totally simple because everything is square, everything, right? And you don't have to worry too much for the most part. Some things are smaller squares, some things are larger squares, but everything's a square. And everything is inside there is nice and easy. However, we don't live in a square world, right? We don't live like that. So there's more chances you're going to have some kind of visual collision problem if you're using a square to surround an irregular object compared to a sphere, okay? There's going to be more chances, there's more problems. But the great thing about these bounding boxes, and there's two types, axis-aligned bounding boxes and object-aligned bounding boxes, totally different, is that mostly we use AABB, axis-aligned bounding boxes. The difference between the two is that object-aligned bounding boxes, instead of world space, the axis, we're using the object, local space, to do the collision detection, okay? So what does this mean? What is this idea of axis-aligned bounding box? Well, imagine if I put a box around an object, right? And I want to basically say, hey, from the top left corner to the bottom right corner, out of there, if I kind of, collide anywhere inside of there, if I intersect anywhere inside of there, I've got a collision, right? But it's rough. It's a rough calculation. Now remember we talked about broad phase and narrow phase? Sometimes we use axis-aligned bounding boxes to do the broad phase, right? Remember that there's many different techniques for doing collision detection, right? So imagine if I have this big room again, and I want to see if I'm colliding with James, right? What I can use is an axis-aligned bounding box to say, hey, if James is not within this boundary, right? Don't check collisions. I've kind of done a collision check already, right? But it's a way easier collision check and much lighter, right, than doing a collision check, between distances. Bye. Take care. All right. So here's an example of some code that you can do that. I have a box, some kind of rectangle. Here's two rectangles, right, with 5, 5 is where it starts, and 50, 50, the height and width of the actual object. And I've got 20, 10, and 10, 10 for my width and height of the object, right? So this is my locations in space. And then what I'm going to do is I'm going to check each of the objects' heights and widths, right, to check that there's a collision. Notice I'm doing 4 different checks. 4 different checks. So I'm saying, hey, if rect1.x, the x coordinate of the first rectangle, whatever that is, right? So that's 5, that's top left corner, as an example, right? Is less than rect2 plus the rect2 width, right? And I'm going to do another 3 checks for each of the other corners, right? Then I'm good to go, right? I've checked all the corners to see if I'm colliding from the top, the right, the bottom, and so on, right? And this is fine. But there's a problem with this type of AABB collision. And again, it's back to what we talked about before. So for this example, I'm going to use fireworks. Okay, so here's fireworks. I'm just going to take this out of there. And I'm going to use 2D instead of 3D. So we'll make a screen that's 640 by 480, right, as an example. Okay, here's my screen. And I have a couple of objects I'm going to put on my screen. So let's use some kind of rectangle. So here's my rectangle, right? Fireworks. Yeah. And yeah, it's okay. And this is my lips, right? Which I'm going to make some kind of object like this. And okay, and let's make my my circle. Let's make it a different color. So we'll just make it green. Right there it is. And we got a little bit of, you can see it. I'm going to put this object. Oops. I'm going to put this object here. This one right here. I'm going to move it inside here. And you know what? Let's make it a little bit smaller so it fits. So it kind of fits inside. I'll make it like this. Okay, cool. And for whatever reason, let's make a duplicate of it. So I'm going to kind of copy and paste it. Here it is. And let's make that smaller too. So I'm making some kind of other weird character. Okay, so I'm making some kind of weird object. Maybe I have an object that's like this. Cool. And now I have another thing, right? And let's just make another object here just to give you an idea in 2 and 3D space. I'm going to make a polygon. There we go. Make it maybe like this. So it looks like some kind of spaceship that's pointing up. There we go. There's my polygon. Cool. Here's my spaceship, right? And my spaceship has to have a box too, right? So let's just copy this box here. So copy and paste. put it over here, and let's make this go to the front. So we'll just arrange it so that it goes to the front, bring it to front, so it kind of layers on top. There it is. Ooh, yay, right? Got two objects. They've been surrounded by bounding boxes, which is what I'm telling you to do, right? And what I want to do is I want to group these objects together, and I want to group these objects together just so that they respond properly. There we go. We got two objects now. So I can move this object together. Now, and I've done this before, guys, so please forgive me if you've seen this example, and you probably saw it somewhere else, but is there a collision here between these two? Yeah, there is, right? Because my bounding boxes are intersecting, and so using AABB collision, there's a collision, but guess what? Look how far away my object is. Now this is a bad bounding box, this one here, right? But even if you made it closer, it still wouldn't be that much better, right? I've got a situation where I don't have a visual collision. The green object is my real object, and my black object is my bounding box. I've got a logical collision, but not a visual collision. And this is a problem in game. It provides a poor visual experience, right? Similarly, if I do this, right? I'm not colliding, but now I'm finally colliding, but it takes me to overlap my bounding boxes. Now, some people argue that you can have smaller bounding boxes. So there's parts of the object sticking out, right? And then you have the other problem where you should be colliding. You're seeing a collision, but it's not really colliding, right? There's no logical collision. So whether you're doing it one way or the other, it's easy, but it's not the most efficient, okay? Now, what you could do is you could combine both the circle idea and the bounding box idea, right, together, where you have both a sphere collider or circle collider plus a bounding box, and you do these multiple checks. But imagine if you had two of these checks happening, right? Whenever I do any kind of less than or greater than, that's also a branch, right? When I do that kind of stuff, I'm doing some kind of branching. Branching is also computational, right? There's some kind of computation that's going on in the system. When I do branching, checks if this one is this one, and if this one is that one, else this one is this one, right? When I start doing these computations, right? And if I'm doing it for every object on the screen, again, if I only have 30 objects on the screen, it's going to be okay. But if I have thousands of objects on the screen, I'm doing 2 checks for every object. If I have 1,000 objects, that's a lot of checks, right? Because you're not just doing 1,000 checks, right? If every object can bounce with every other object, for example, I don't know, some kind of weird particle collision system or something, right? It's going to be really computationally expensive. You need to have a very efficient system. And this, my friends, not the most efficient. All right, so does everyone understand the difference between visual collision and a logical collision? You should by now, right? And this is the idea. We're only talking about collision detection today, all right? How do I detect collisions between two objects in 3-dimensional or even 2-dimensional space? Okay, great. So that's AABB. And if you don't know that, if you haven't learned that from before, you know it now. Okay, this is kind of the code that you would use. You can see that they've just subbed in the the values that we've got from our x's and y's, and you can see that if all of these are true, all of these cases have to be true for there to be a collision with AABB type collision detection. And again, we can use AABBs for 3D. I'll be honest with you, they're more catered towards 2D type detection because of, right? We have sprites in 3D, in 2D. We don't have sprites in 2D typically. Or 3D. We have polygons in 3D, and we have polygons. You already have a shape, and if you already have a shape, you can start thinking about, hey, can I use my shape of the polygon itself to start doing a collision? Now, you don't want to use the mesh of the polygon. For example, if I make a very some kind of organic character shape, and I want to use each of its vertices to check to see if I'm colliding with you, that's inefficient. All right, there's too many checks going on if I check each vertex or each other one. What was that?
What about the football game? Like where like it's that hand, arms, and wrists as opposed to like a sphere.
Again, I might use a very close approximation in terms of basic primitive objects to surround my arm or wrist or hand. A lot of times it's good enough, right? Now in the future, as our CPUs and GPUs get faster and more powerful, hopefully they will, right? When we don't have to worry about these things as much, you'll start seeing more and more mesh type collision detection or some kind of collision cloud where you have a bunch of vertices And if you're in that, you're inside that space, you collide. There's different approaches, other more scientific approaches to doing this. But one of the most complex approaches to doing this is something called using separated axis theorem. All right. So separated axis theorem is an idea that's a little different, and I've got to introduce it to you. I don't expect you to remember it as much, and personally, I don't use it for the most part, and I'll tell you why. It's complex to set up. Okay. It's slow at times as well. Depending on how you're using it, it can be very slow because now in 2D space, okay, I'm only checking up every side of my object, let's say. Now this, I'm looking at, as an example, these, squares or rectangles, if you will, right? And all I need to do is check if there's some kind of axis, a line that I can put between the shapes. And if I have a gap between the space, the shapes in any axis, whether it's to the side or to the top or whatever, then I don't have a collision. And if I don't have a gap, then I have a collision. This idea of that, right? So if you look at what it says if you're able to draw a line to separate two polygons, then they don't collide, right? That's really what separated axis theorem is about. 2D, it's okay. It's pretty heavy to program. And if you're going to do that in 2D, it's like crazy. But in 3D is where it really makes sense, right? In terms of accuracy. If you want to be dead accurate, you want to have a football game where you need to see the fingers touching the ball, then separated axis theorem is probably more efficient than a mesh collider, right? Because you can use the normals of each of the faces of the objects, the polygons that you're using, to detect if there's a separation, some kind of axis separation between the two objects. So, most complex way of doing it, okay? Now, it depends on the user. Some people, there's a bit of controversy because when it comes down to it, some people think that separated axis theorem is the way to go. We should always use separated axis theorem in the most accurate way, but it's not the most efficient way. Remember, the most efficient and simple way is sphere collider. Simplest way, right? And it's still, for the most part, is good enough for most little games, right? Imagine if you took this into a 3D space, right? So each side is not a side, it's a face, right? Now you're separating faces, the face normals, right? As opposed to the sides. In this particular case, it's just 2D. Okay? So the way they explained it here on this website, which I kind of found a website that kind of explains it really well, and that's why I've given you the link for it, so you can actually read at your own leisure. I'm not going to go too much in detail here, because separated axis theorem I'm going to talk about, but I don't expect you to, I'm not going to talk about in detail. The two that you should be using is AABB for the most part, and sphere collider or distance collision. Those are the two that you can combine and make almost any collision pretty good, all right? Like the capsule collider idea. But here's an example of this guy that kind of pictures separated axis theorem as an idea of this shadow. I want to take my edges and I want to project my edges down onto an axis somewhere, right? If my axis is not on the ground plane like this, I can rotate and adjust, translate my axis, right? Normalize my axis so it appears like this. And then what I'm going to do is I'm going to take my two objects and I'm going to project both of them in the same direction, right, on an axis. I have to do it from all sides though. So if they collide from all sides, then we have a collision. If they don't collide from all sides, we don't have a collision. If they don't intersect, the shadows, the projections don't intersect, right? We don't have a collision. Understanding this is one of the problems. People don't understand it. But there's some really good points here about how this works. So all sides some side, you can't have a gap anywhere. If you can separate the two objects with some kind of line or a plane in 3D space, then you do not have a collision. If you can separate them somehow, right? So here's step one, and this is how they talk about it. I test this side, right? Here's the axis we're going to project onto, right? And what I want to do is I want to take this axis, right? And I want to find the normal or perpendicular vector from it. Right now we're talking about normals again, okay? And this is quote unquote the axis. All right, cool. I want to project my axis down to some perpendicular. I'm going to take the perpendicular from the axis, whatever that is, right? and I'm going to project it down there. All right. Now, if you notice, I'm creating this line of this axis line right here. I'm actually creating by taking the perpendicular to this particular line here. So here's my line segment, and my perpendicular is the axis. This is 90 degrees to the line segment. Okay. So that's what the second part that I do. Third part, I do the same things with my other shape, right? Based on the original shape's axis that I created, I take the other shape. Notice that there is a separation between these objects and these objects. Therefore, no collision. It's very simple, right? So instead of having cubes, I can have other kinds of objects. I can project all the points down on an axis. And then I can use math to kind of dictate, hey, do I have a collision? This is very accurate. But with multiple polygons, I may have to write a function that tests every surface of the polygon, right? So I can check 2 polygons. I'm going to know that there's no collision. But one thing I won't know is which one, if I do have a collision, I don't know which one I'm colliding on. I have no idea. Why is that? Because I'm projecting them down. I don't know which one it is, right? It could be this one, it could be that one, it could be the other one. I don't know which one it is. And so that's kind of a negative from a separated axis theorem. So those are the pros. Pros are it's pretty fast overall for this kind of complexity. Basic vector math, it's not that difficult to figure out if you have the code. I'm going to give you the code. It's fair. It's really accurate, especially for 3D. It's great for simulations, right? On the bad side, it only works for convex polygons. What does that mean? That means anything that stands out. If you have a polygon with some kind of cave, concave, like this, some weird shape of a polygon, it won't work, right? And that's a problem. That means it's not for everything, right? It's not every type of method is useful everywhere, and that's why we combine methods when we want to detect stuff, right? All right, and the other part is it doesn't tell you which sides are touching, only how far they're overlapping into the shape. So here's the idea. I have these 2 objects. They're boxes, and some old code. This is actually AS3 action script, right? It doesn't matter. It's just I want you to think about it as pseudocode. All right, it could work on any system. I've got these 4 boxes, and what I'm doing is I'm defining these dots. Each of the dots is I've got the center of the object as well as each of the edges of or each of the vertices that make up the object, right? And I've named these dots dot 1, 1, dot 1, 2, and so on. Dot 1, 3, dot 1, 4, and that's for box number 1. And box number 2 starts with 2s. So 2, 1, 2, 2, 2, 3, 2, 4. Of course, 2, 0 is the center point, and 1, 0 respectively. And then what I want to do is I want to kind of have this idea of I want to define the vectors. Now, again, think about this as pseudocode. Whether if I have some kind of vector library, what I want to do is declare 2 objects, 2 vectors. One that is a box 1 is you can see that it is an array of type vector 2s, right? And here's another one on line 6. It says a vex box 2. These are all the vectors for an array of vectors for box 2. This is again old pseudocode, right? And then you have a for loop, and what you're going to do is you're defining 2 corners. The corner for box 1 and the corner for box 2, which are 2 points. So they're probably a vector 3 object or vector 2 object. It doesn't matter. And then what I'm going to do is I'm going to get each of the, when it says get dot, it's just a method that gets each of those dots. Where are those positions, right? And I'm basically building up all the corners of the boxes. For each of the corners of the boxes, I'm getting the dots related to that particular corner. And then what I'm doing is I'm testing them. I'm saying, hey, push each, when I say push, I'm going to add that particular corner of that dot, which is up here. I'm going to push it onto the vector array. That's what I'm doing. So I'm making an array of vectors. I'm pushing each of these locations onto the vector array. And once I've done that, right, I can start kind of doing some of my checks, right? So what I want to do is kind of find the minimum distance. I'm going to start projecting the projection of each of the edges, right, down to the axis. That's what I'm doing here. I'm not going to explain too much more about this because I'm going to lose you in a second. You're probably already lost. And the final part is I'm checking to see if it's separated. If the object is separated, then I have a gap. And I'm checking to do that by saying something like this: my projection of box 2, if it's less than the projection of box 1, or if the projection of box 1 is less than the projection of box 2, that's where we cut it down to, we have a collision. All right, that's the idea, right? This is separated axis theorem. It's a very basic, very basic way of doing it. Yes.
The get dot function.
It's just a function that basically gets each of the dots on the points on the thing. That's all it is. Don't worry about what it is. It's just pseudocode, right? So it's not a built-in function that's part of ActionScript or anything. It's just a function. If you really want to see the code, again, I recommend you go to the site that I quoted. You can download the source code yourself. It's pretty simple, but I wanted to talk about it here because at the very basis, you can see that there's a lot more code here, right? Lots of setup. I've got a lot of setup here to go to provide, to test 2 boxes, right? Now, typically what I would do is I would make a class, a collision class, and start, checking my collisions to make it more efficient. That's all I really wanted to cover today in terms of detection. I've talked about, just to sum up, I've talked about really 4 major methods of collision detection. The one that's easiest is sphere or circle collider or distance. That's the same thing we're talking about, which is Euclidean distance, right, between 2 points. And if the distance between 2 points, right, is less than the combined radii, right, of the circles that make up the boundary, we've got a collision. That's collision type 1, okay? Collision type 2, second simple way of doing it, AABB collision, right? Axis aligned bounding box, right? Now, one thing I should mention about axis aligned bounding box is if I rotate my object, I need to redo my box. That's one thing I need to do, which is a little bit complex sometimes. What do I mean by that? Well, if I go back to fireworks for a second, I've got this object, right? So let's suppose I rotate this object now. So I'm just going to rotate it like this, right? Does that bounding box make any sense anymore? And the answer is no. It has to all be axis aligned, world aligned, right? Which means I have to redo my bounding box, right? My bounding box can't be this anymore, right? I'm just going to ungroup here. If I can, oops, let's try that again. I'll redo that. I have to ungroup for a second, and I'll show you. If I want this bounding box itself, it has to align the way it was before, right? So we're just going to make another bounding box. You can see that I've rotated everything, right? And what I want to do here is let's make another bounding box the same way. So let's make a rectangle, and we'll make it so that it is, even though the object is rotated, right? I'll make my bounding box change size like this again, and I'll just send this to the back. So you can see that the bounding box has changed size, and it'll keep changing size, especially if my object is really long. If I have like a really long spaceship, like for example, if I was going to make a Star Trek game, and I have the Star Trek Enterprise, it's kind of longer, right? It's not wider, right? And as I move, I want my bounding box to kind of surround this object, right? So as I rotate my object, if I'm using axis aligned bounding box, I've got to recast my bounding box. It can't be any more of that, because what's happening is it won't be axis aligned anymore, and I can't do collision detection. It always has to be axis aligned, okay? Which means, hey, what's the leftmost point? Okay, that's the top left corner. Hey, what's the rightmost point of my sprite? That's the right corner, right? Hey, what's the top? That's the top part of my box. Hey, what's the bottom? That's the other part of my box. And you have to keep doing that over and over again. You have to kind of translate your bounding box as you move your shape, which is another challenge sometimes.
So would that be the same for when it's animating? You want to recast
Yeah.
your bounding box
Yeah.
when it's animating?
Absolutely, and it does it
For
automatically.
example, like if the rabbit was running, it's probably going to longer.
Yeah, so you have to
Bounding
recast,
box,
you have to
right?
redo your bounding box every time so that it's more accurate. And what's going to happen is that's another calculation you have
That'll
to
be
do.
the more efficient way to do it.
More efficient, but it's more calculations, more things to do, but less work than separated axis theorem. Okay, so the third one I talked about was a mesh collider. We didn't see it in action, but we talked about a mesh collider, which is dead accurate, right? I'm going to have as many of those points. I can put many points all over my object, and I can check the distance between each of those points with other objects. Woohoo! That's a crazy amount of checks, right? Which is nuts. Yeah.
You code it.
every point. I'm going to loop through each vertex, right? And check to see the distance between those points, right? Nuts. And then the fourth one is separated axis theorem. I talked about that, right? Which is the most complex kind of to code, to set up, right? Accurate, it's fairly fast, and we don't normally use it unless we absolutely must between the two last ones, right? Because and now again, this is the great thing about coding. It's like a buffet, right? Like a Chinese buffet, you can take what you like and leave the rest, right? Because, or I don't know, any kind of other buffet nowadays, because if you can use a mishmash of all of them. If I want to use a bit of axis line bounding box for square objects, right? And I want to use some kind of distance calculation for the other object, I can do that. How do I do that? That means I must have some kind of, sphere and a, kind of prism collider happening. I got to create that, right? Which is very close to axis line bounding box, right? And I can create those things. And if you look on the web, there's different things. For example, sphere in a line, sphere in a plane, right? And so on. And there's a lot of other ways of collecting or detecting collisions. We also talked about narrow phase and broad phase, And remember, we talked about narrow phase and broad phase because I can't possibly collide with objects way far away from me in space, right? And I want to be able to see where they are. And so what I do to help me, and this really helps from a collision perspective, is I grid everything. Now the grid has an overhead, right? If I create a grid and I place a matrix, right? Really is what I'm doing, across my entire world space, right? Now I know where everything is, right? I know. And I know what occupies that grid space. The smaller the grid space, the more accurate and more calculations I need to do because I have more cells, right? But if I have a grid, if I divide this room into grid cells of 1 foot by 1 foot, imagine these 1 foot by 1 foot squares everywhere in this room. I block out this room with these imaginary squares, right? Then I can get as close to a foot of accuracy, right? And I know that where you are within a foot of me. Now, when you want to do more complex calculations, for example, pathfinding and so on, and you're going to probably get into that with algorithms, right? At some point, you can kind of determine how far away the object is by using some simple calculation like an A-star pathfinding, as an example, right? So that can be part of your broad phase calculations. And if you have enough objects, it makes sense because the overhead for that is much less than the overhead for doing calculations for every object on the board, right? Okay, question. You had a question.
Yeah, so important to all this calculation.
Circle collider?
Yeah.
So Unity has a bunch of different colliders, but at the base end, if you think about what they're doing all this stuff, right? One thing that Unity also has is something called continuous collision detection, right? One thing we didn't talk about here, we didn't have a chance to talk about, we're going to talk about next week a little bit when it comes to collision response is, how about bullets, right? I got this bullet, and it's really, really small, right? Right now, we're talking about shapes that are approximately the same size. So here's something of a thought to leave you with, right? If I make another object, so here's an object. I'm going to make a ellipse object, and it's going to be fairly small. So let's make this object fairly small here. There it is. This is my bullet, right? And let's just color code it a little bit differently so we can see it as a different object. There it is, a red bullet, right? It's really, really small. Okay, cool. Am I colliding? How do I obviously I'll make it a circle collider, right? Or some kind of, even a rectangular collider, AB collision, right? But it's so small, right? So it has to be really close for it to be colliding, like really, really close, right? Now, if I have a box collider, it's going to collide here. You're going to see it collide there. So it's going to disappear around here, right? If I use what was that? You will have an explosion. If it's fast enough, it'll be good enough, right? But what if I'm checking for the frame? This thing is moving very, very fast. So let's suppose I'm moving at something like, okay, right now by the way, just to give you a sense of what this thing is, the width of this thing is about 11 pixels, okay, on the screen here, 11 pixels. I'll make it bigger so you guys can see it, right? So let's just make it really big. So there's my 11 pixel object, right? You can see that it's pixelated now that I've come close, right? And I'm going to move 40 pixels every frame. Okay, so here's my object. And again, I'm approximately 11 pixels. So 40 pixels about right here. Did I collide? No. How about now? Did I collide? No.
way inside of it.
How about now? Did I collide? Yeah, we're good. Now, what about if it's really, really fast and really small, and we're traveling at about 100 pixels per frame? Okay, 100 pixels. Did I collide? No. Okay, wait. Hold on a second. And this is the tunneling effect we're talking about. Did I collide? No. Because I'm checking to see if it's inside the other object, if it's overlapping. There's no overlap, and therefore I don't have a collision, which makes it so that I have my object seeming to tunnel through the other one. This is the tunneling effect of bullets. Now, there's ways of figuring this stuff out. One of the ways is to project a rectangle in front of my bullet that I'm checking as well, right? Now, remember, if there's thousands of bullets, imagine a bullet hell game, right? And I want to be dead accurate somehow. I don't know, right? That means you're going to do a lot more checks for bullets than you do for other objects, right? So again, you'd use a combination of techniques, and what you want to do is through trial and error, through experimentation, you want to come to a point where it's good enough. Yeah. Well, yeah. I mean, you're basically saying, hey, this is one way to do it. Is hey, where I'm traveling at this particular speed in this direction. Where am I going to be next frame? I'm not only going to be here, but let's suppose that.
You never do check with a high number.
Right. Where am I going to be next frame? Let's say I'm going to be probably here next frame, right? I'm going to collide next frame. Okay, how about this? I'm going to be here next frame, right? I'm so fast, I'm going to be over here next frame, right? But there's an object in between. There's an object between me and the line between where I am and where I'm going to be. There's some kind of something in the middle between me and the other object. I'm going to collide. You see, so there's ways of doing it so that you can make an algorithm so you don't have to tunnel through, right? Now, I'm not going to tell you this is the optimal solution because this will fail as well based on if the other object is moving. For example, right? My object is stationary, right? But what if the other problem is my object is also moving? So I'm predicting that it's going to be here, but this object is going to be down there. So is there going to be an object next frame in this space? Yes or no? That's a different question than, am I going to pass through an object that I'm going to be interrupted from, right? So I'm proposing these issues that you can fix with code, right? It takes experimentation. There's some solutions on the web. People will look to see these problems, but bullets and other objects, small objects, tunneling that are very fast is always a problem. Okay, it's always going to be a problem until we find other kinds of algorithms we can use to predict their path. Okay, any questions around this stuff? All right, so very simple stuff today, guys. Remember that there's no lab today. All right, so we don't have a lab today. We do not have a lab on Thursday, so please don't come on Thursday. I will not be here unless you make arrangements with me to meet with you guys. There's no lab today, no lab Thursday. And remember, next week there's no test. All right, so we don't have a test and there's no assignment. Okay, so please take a look at that for those people who came in late. Okay, we will, however, do collision response next week, which I will be here to talk about on Tuesday and during lecture class. Okay, any questions before we leave for the day? Guys, have a great day.